Okay, so today we're going to be looking at kind of a short intro here into 6.3, starting with binomials. And so let's look at our problem here. In the 2005 Conference USA basketball tournament, Memphis trailed Louisville by 2 points. At the buzzer, Memphis's Darius Washington attempted a three-pointer. He missed but was fouled and went to the line for 3 free throws. Each made free throw is worth 1 point. Was it smart to foul? So the first question here asks us, what are all the possible ways the shots could fall? Basically, it's asking you your sample space, right? So he could have made all of them, right? He could make the first two and not the second one. He could make the first one and not the next two. He could make the first one, not the second one. He could make the third one. Okay, he could miss the first one, but make the next two. He could miss the first one, make the second one, and miss the last one. He could also miss all of his shots. Okay, and then which one did I leave out? I left out that he could have missed, and made it. Okay, you also could have done a little tree diagram to go from this, right? His first shot, he either makes it or he doesn't. The second one, he either makes it or he doesn't. The third one, he either makes it or he doesn't. And you could have done that all the way through to help determine your sample spaces. Okay, so number 2 here then, Darius Washington was a 72% free throw shooter. Find the probability that Memphis will win, lose, or go to overtime. When you have found the probabilities, put them in table 3. So his probabilities here that he could, that he's going to make each shot is 72%, okay, or 0.72. So go back to your problem here. Remember, they trail by 2 points. The only way for them to win is for him to make all 3 of his shots here. And so for him to make all 3 of his shots there, the probability of that happening is 0.72 to the third, right? Or 0.72 times 0.72 times 0.72, right? The probability of the first shot times the probability of the second shot times the probability of the third shot, which gives him 0.373. The probability that they lose, okay, so for them to lose would be no makes. So this one right here would mean that they lose it. He scores no points. Okay, so my probability here is 28, again to the third, which is 0.022. They would also lose if he only made one of his shots. So there's 1, 2, should be, oh, I'm sorry, that one. There are 3 options of him losing. Sorry, I had circled the wrong one for the missing all of them. So there are 3 options for him with 1 make and 2 misses. Okay, and so that's 0.72 is 1 make, and then a miss, and then a miss. But that's going to happen 3 times, right? So that gives us 0.0. I'm sorry, not 0.0, 0.16, let's go with 0.169. Okay, and then, so we would add those 2 together, right? So we would add the 0.022 and we would add the 0.169. So add those 2 together for your overall probability of them losing. And then the probability that they go to overtime would be a tie. And so for a tie, he would make it 2 times, times 0.72, and he would miss it 1 time. Okay, and again, there are 3 ways that that could happen. And so that probability gives us 0.435. We will break down the formula for this part right here on your formula chart together in class, because the formula looks kind of crazy. Okay, so let's go on to part 3 here then. Prior to watching each shot, calculate the probability that Memphis wins the game in regulation loses the game in regulation, or sends the game into overtime. Okay, so his first shot, he's taken no shots, so his probability of Memphis getting a win is still intact. It's still 0.373. He could make all of his shots. Okay, the probability of Memphis losing, we're going to need to actually add the two together, this 0.169 and the 0.022 that we had before, so we get 0.191. Okay, so that's the probability that Memphis loses. And then the probability they go into overtime is the 0.435. That's the probability of him making two of the shots but missing one of them. So he takes his first shot and he makes it. So now Memphis has 74 points. So now, before he takes his second shot, what is the probability that Memphis will win? Well, he needs to make both of his shots. So the probability that they will win is 0.5184. The probability that they will lose means that he doesn't make either of his shots, because right now we're at 75/74. So that would be 0.28 times 2 squared, right? So 0.0789. And then the probability that they go to overtime is going to be he either makes a shot and misses a shot, then makes one, or makes one and then misses one. So either way, I'm doing his make probability times his miss probability, and that's going to happen. That has two chances to happen. So our total probability here is 0.4032, that they end up tying it and sending it to overtime. So now he takes his second shot, and he misses his second shot. So now they're still at 74 points. There is no chance for Memphis to win right now. Okay? Even if he makes the shot, they won't get 76 points. They'll still have 75 points. So there's no chance for Memphis to win. The probability that Memphis will lose is him missing the shot, which is 0.28. And the probability that they will go to overtime is him making the shot of the 0.72. And now Darius takes his third and final shot, and believe it or not, he misses it. Okay? And so Louisville ends up winning the game 75/74. So looking at question 4 then there, Washington is a 40% three-point shooter. Do you think Louisville was smart to foul? Why or why not? So think about what that's asking you there. Okay, so with 2 seconds left, that guy was going to take a three-point shot, which would have made Memphis win the game had he made it. But normally he's a 40% three-point shooter, and he's a 72% free throw shooter. So do you foul him or do you not? Okay, the probability that Louisville will win if they do not foul him would be 60%, right? 60% chance he misses the shot, Louisville wins, we're done. Okay, they have a 40% chance of losing, that he'll make the shot. That'll give them 3 points. They'll win 76/75. Then you have to decide whether to foul him. Okay, so you run the probability of fouling him, okay, and you work through the calculations that we just worked through. And so my chance of losing in overtime, I run that risk then of going into overtime and possibly losing there. But my chance of losing in regulation actually goes down. For him to actually make all 3 shots in a row is actually slightly less than for him to make the shots, for him to make the 3-point shot. So that would be the coach's decision as to whether that was a good idea or not to foul him. Okay, so let's wrap up what we saw happen in that last problem. So what you saw happen in that problem, we had 2 kind of major things happen. Okay, we're going to put idea number 1 on this side and idea number 2 over here on this side. So the first thing that you saw is actually the setting for a binomial problem. Okay, so whether you realize it or not, you saw the characteristics of a binomial problem. Okay, and so the characteristics of a binomial problem are the fact that it's binary, a success or a failure. Okay, a check or a minus. He makes the shot or he does not. Okay, so a success or a failure. That would be the character, that would be that's what it means by binary there. Okay, so he either can do it or he cannot. There's no in between. The ball doesn't go halfway in and then, stop. Okay, the events are independent of one another. His first shot is independent of his second shot. Okay, his third shot was independent of this first and the second. So the events are independent. There is a set number of trials. In this particular case, he had 3 tries. And this is going to be part of our formula. We're going to see this pop up just a second. We're going to look at the formula. So a set number of trials, which in our formula is a lowercase n, kind of like our sample number was before. And then that it all has the same probability. It didn't change. So his probability of making the shot did not change as he did different shots. It's not like, think about when we did the card example and our probability of drawing a heart on the first card, and how if we returned that card, the probability stayed the same. But if I didn't return the card, that affects my probability. Now my probability is out of 51 cards instead of out of 52. Okay, so in this case, in a binomial setting, the probability stays the same every time. Okay, it stays at that 0.72, and in our formula, that's our lowercase p in our formula. So let's look at this formula. I know we said we'd look at it in class, but let's go ahead and look at this formula. Okay, so the formula is the one on your formula chart, p parentheses x equals k. Okay, and so what this will look like, okay, is we have n, c, k. See if I can fit all this on the iPad. Okay, and then 1 minus p to the n minus k power. And that looks like something horrible, right? I mean, that looks like a horrible, horrible, awful formula, right? But let's think about it. Let's talk about what we put over here in the binomial description here, right? N is going to be my total number. So in the case of that first problem, it was 3, right? He had 3 shots. Okay, K is my number of successes. So that's what you're looking for, the probability of successes. So let's say we're solving this one for his two makes of the shot and 1 miss, that going into overtime situation. Okay, so P is my probability of success, the capital P here. Let's see if I can fit that in anywhere. So the capital P is my probability of success. Okay. This portion here is my probability of failure, 1 minus P. Okay, so in our basketball example, that would be the 0.28. And then the n minus k, n is still my total number, and k is my successes. So then I have my capital C here in the middle that we didn't address. Okay, that's for our combinations. That's my notation for the number of combinations of R things. So for example, K things, so my K successes. Okay, so my number of successes is 2, my different ways that I could get 2 successes out of 3 total shots. This is the notation you can use on your calculator, and you've probably seen that in math class. Your formula chart shows it written N over K, which is a newer form of notation, and I don't know which one you've seen in math class, so this way you can see both. So if we were plugging this into the example that we saw on the other side, right, he had 3 total shots, okay, and then our combination of trying to get 2 successes there times my 0.72, my probability of success, and I needed 2 successes, times my probability of failure to the 3 minus 2, so to the first power. And that gives me that 0.435 that I got on the other page for him, possibly for him bringing it into overtime, for getting in the tie, since there were multiple combinations of ways that he could have gotten that. So if you're trying to decide if you're going to use this formula for a binomial, keep in mind you need to check, is it binary? Is there success, failure? Are they independent of one another? Do I know a set number of trials? Okay, and do they all have the same probability? And then I can go ahead and use this formula, which I know looks kind of crazy, but hopefully now that we've kind of shown it in context with this example, it does not so much. So let's look at this problem here. Let's look at one more example. For each of the following situations, determine whether or not the given random variable has a binomial distribution, and you'll need to justify your answer. So let's look at part A. I shuffle a deck of cards. I turn over the top card. I put the card back in the deck and shuffle again. Repeat this process 10 times. X equals the number of aces that we observe. So let's go through our little acronym here. Okay, is it binary? Do I have successes and failures? Okay, in this particular case, right, a success is that I got an ace, right, and a failure is that I did not get an ace. So I have successes and failures. Okay, are the events independent of one another? They are because of replacement. Because I'm putting that card back in there, I am not making one draw of the card or one flipping the top card over on one does not affect the next card that I'm going to flip over. Okay, is there a set number of trials? Well, I'm doing it 10 times. Okay, and then the last part there, the S, is it the same probability? Yes, it is. Since I am using replacement, I have a 4 out of 52 probability every single time that I do it. So this one does fit my criteria for being a binomial distribution. Okay, looking at letter B here. Choose 5 students at random from your class. Let Y equal the number who are over 6 feet tall. Okay, so is it binary? Do I have a success and a failure? Okay, yes, I do. Right? They're either greater than 6 feet or they are not. So I have success and failure. Are they independent of one another? Okay. No, they are not. Because I am not doing replacement, because I didn't send the student back into the sample every time, these events are not going to be independent of one another. Therefore, it does not fit our criteria for being binomial. Let's look at the second problem here. Pedro drives the same route to work on Monday through Friday. His route includes 1 traffic light. According to the local traffic department, there is a 55% chance that the light will be red on a randomly selected day. Suppose we choose 10 of Pedro's work days at random and let Y equal the number of times that the light is red. Okay, so let's see. Is it binary? Is there success and is there failure? Okay, well, the success is the light is red, and a failure would be that it is not red. Okay, it does meet the criteria of being independent. There is a set number of trials, that would be 10, right? And the probability stays the same. So I have the same probability all the way through, which is 0.55. So now I'm asked to find the probability that the light is red on exactly 7 days. Okay, so in this instance, I'm looking for the probability that the light is red on 7 days. Okay, K is my number of successes here, right? So when I plug this into my formula, I have my N, which is 10, combinations, and I want 7 successes, times my probability of success to the 7th power, because that's my successes, times my probability of failure, which would be 1 minus 0.55 or 0.45. Okay, and that is to the n minus k power. So to the 10 minus 7 power, which would be 3. So if you plug that into your calculator, so when you go to your calculator, go to the math button, So you've hit math, which is 2 under the second button there. So hit math, arrow over to probability, arrow down to number 3, where it says NCR. Okay, in the lower box there, type a 10, arrow over, and that will take you to the box that's on the right of the C where you can type a 7, and then arrow over again. Type in your multiplication, 0.55 to the 7th power times, oops, let's leave that, times 0.45 to the 3rd power. And that will give you 0.1665. And if you had trouble putting that into your calculator, I can help you with that. That's not a concern. We can walk through that in class. Okay, so that was our goal today, was to be able to use that formula and to be able to recognize what a binomial problem looks like.